Hi everyone, we will continue our discussion on cheminformatics. In the previous lesson, we explored synthesis planning using a molecular transformer, which uses AI used in language translation to chemical reaction. In this lesson, we will focus on another approach used for the forward synthesis prediction. This method uses enhanced graph neural network, and the method is referred to as reaction-aware molecule representation learning. The material is based on the journal article written by Wang et al., published in an open access preprint repository, ARXIV, in September 2021. Let's do a quick review of what we have been discussing. Synthesis planning is the process of determining how to synthesize a specific molecule. Forward synthesis planning is also known as forward problem. It answers the question, what will be formed if these specific starting materials and conditions are brought together? It involves predicting the product of a chemical reaction given the reactants and reagents. Organic synthesis is rarely a single-step process. It is almost always a multi-step process. Forward synthesis planning is crucial for designing these complex sequences, where the product of one step becomes the reactant for the next. The computational algorithms are generally fall into two categories: template-based method, template-free method. In the template-based method, recent machine learning approaches started to automatically extract template libraries from reaction database. However, seemingly automatic techniques rely on handcrafted and often highly specific chemical rules. To overcome this limitation of template-based method, template-free method has been developed. It can be further categorized into graph-based and sequence-based. We have discussed sequence-based template-free method in the previous session. In this session, we will discuss graph-based synthesis planning. Before introducing MolR, let me briefly highlight the challenge of representing molecules for AI. In cheminformatics, one of the biggest hurdles is how to represent complex three-dimensional molecules in a form suitable for AI and machine learning algorithms. This is where molecule representation learning, or MRL, comes in. MRL works by embedding molecules into low-dimensional vector spaces. These embeddings, or learned vectors, capture essential chemical information in a compact form. With these embeddings, we can unlock a wide range of downstream applications, such as chemical reaction predictions. We have seen the example while learning about molecular transformer. That involves enhanced sequence-to-sequence model. Retro-synthesis planning. We have also seen the example while learning async finder that involves Monte Carlo tree search algorithm. In several of previous lessons, we also discussed molecular property prediction, such as boiling point prediction. Also, in the bioinformatics lesson, we also discussed protein ligand binding affinity prediction. Lastly, in one of the bioinformatics lesson, we also discussed drug discovery. And these are some of the downstream applications using embeddings. Wang et al. Developed MolR, a framework that integrates chemical-reaction-aware molecule representation learning. He discussed this code in his publication in ARXIV in 2021. Here is the key idea. GNNs struggle with generalization, but we can improve this by letting the chemical reactions guide the learning of molecular representations. The core principle is simple. We want our embeddings, which is the way of digitization of molecule in a vector space, to respect chemical equivalence. Molecules that participate in the same reaction should relate consistently in the embedding space. In other words, core principle is to preserve the equivalence of molecules with respect to chemical reactions in the embedding space. How do we do this? For each chemical reaction, we force the sum of reactant embeddings to match the sum of product embeddings. For example, take the Fischer esterification of acetic acid and ethanol to form an ester and water. We force the sum of acetic acid embedding and alcohol embedding to be equal to the sum of ester embedding and water embedding. Now we have the constraint. For each reaction, reactant R turning into product P, we enforce that the sum of reactant embeddings equals the sum of product embeddings. What does this do to the embeddings? It makes them composable. In other words, they can be built up from parts. The embeddings of a reaction is just a sum of embeddings of the individual molecules. This means you can construct new reactions directly from known molecule embeddings without having to retrain the model. Now think of the embedding space as being organized. Each reaction, represented by the arrow, groups the molecule sets into equivalence classes. In other words, reactions, which is represented as the arrow symbol, link different sets of molecules, and those linked sets fall into the same bucket or same class. Because their embedding sums are constrained to be equal, the space remains well structured and consistent. More generally, if one set can be transformed into another through a chain of reactions, they also belong to the same equivalence class. Now, how do we apply this constraint in the code? We use a loss function based on cosine similarity. Loss equals to 1 minus average of cosine similarity of reactant embedding and product embedding. It's actually sum of reactant embedding and sum of product embeddings. Why do we use cosine similarity? Because it focuses only on direction, not the magnitude. That way, embeddings are functionally equivalent without being forced to match in size. This makes the learning process more stable and scale invariant. The reaction center is the part of the molecule that actually changes during the reaction. In other words, it is the minimum set of atoms and bonds that are altered. For example, in the Fischer esterification reaction, the orange highlighted regions in propionic acid and propanol represent the reaction center. These centers usually correspond to the chemically active parts of the molecules, what we often think of as functional groups or moieties. A graph neural network, or GNN, works by using layers that iteratively gather information from each atom's neighbors. You can think of it like a ripple effect. With each layer, information gathered from neighbors farther apart from the reaction center. For each atom in the molecule, let's take an atom 1 as an example. The GNN builds its representation layer by layer. Layer 1 collects information from its immediate neighbor. Layer 2 looks further out to the neighbors of neighbors, 2 hops away. Layer K-1 extends this process up to K-1 hops. Once this process is complete, the final embedding for the entire molecule is usually obtained by summing all the atom's embeddings from the last layer. This step is known as summation readout function, shown here at the bottom. The residual sum, the sum of reactant embedding minus sum of product embedding, depends only on atoms within K-1 hops steps away from the reaction center. If the GNN-based encoder is well trained and minimizes the residual for a given reaction, it indicates that the model has implicitly learned exactly what changes and what stays the same at and around the reaction center. This concept is referred to as implicit learning. Let's look at the carbon atom far away from the reaction center here. Since the parts of the molecule far from the reaction center don't affect the change, the knowledge learned from one reaction can generalize to an entire class of similar reactions. For example, what MolR learns from the reaction between propanol and propionic acid can be applied to other alcohols and carboxylic acid. In other words, MolR effectively learns the underlying reaction template. In summary, by equalizing the sums of embeddings for reactants and products, the model naturally focuses on the chemically active regions, the reaction center and its immediate neighbors. This enables it to capture abstract reaction templates instead of merely memorizing specific reactions, which greatly enhance its ability to generalize. And this concept is referred to as generalization. We began with the constraint that the sum of embeddings for the individual reactant molecules must equal sum of embeddings for the individual product molecules. However, directly minimizing this loss function leads to degeneration, where all molecules collapse to a zero embedding. This degeneration arises from the very nature of the constraint itself. The sum of reactant embeddings minus the sum of product embeddings is forced to equal 0 to establish the equivalence. Thus, MolR minimizes the loss function using mini-batch-based contrastive learning. Instead of using the dataset, we're using the mini-batch. In this contrastive learning, matched reactant and product pairs and unmatched reactant and product pairs, I is not equal to J, play a central role in the training process. So, what do we mean by matched and unmatched reactant and product pairs? Matched pairs are simply the reactants and products that truly belong to the same chemical reaction in the training data. These are what we call positive pairs. They are represented as the values in the diagonal matrix in this schematics. Unmatched pairs, on the other hand, are formed by taking the reactants from one chemical reaction and pairing them with the products from a different chemical reaction within the same mini-batch. These are referred to as negative pairs. They are represented as the values other than the diagonal matrix. With that in mind, let's take a look at the expression for the new loss function. The first term in the expression looks similar to the straightforward loss function. The difference is that it now operates on mini-batch B instead of D, using subsets of reactants and products from the training dataset. Just like before, the model's goal is to minimize the discrepancy or distance between the sum of the reactants embeddings and the sum of product embeddings for these positive pairs. The second term in the expression captures the case where I is not equal to J, meaning the reactants and products do not belong together. In a simple chemical term, these reactants are not expected to produce these products. This term measures the discrepancy for such negative pairs and applies a margin, gamma. The distance between unmatched pair must be greater than this margin to be negative value. If the distance falls below gamma, a penalty is applied. In summary, the model relies on positive and negative sampling strategies. This provides essential supervision for optimization and helps structure the embedding space, bringing chemically equivalent molecules closer together while pushing apart non-equivalent combinations. Fortunately, with the help of ChatGPT, I was able to reconstruct a working version of MolR code. Let me show you how it is structured. First, the code imports both standard Python libraries and some external user-defined modules. While I could have included those user-defined modules directly inside MolR_batch_train.py code, I chose to keep them separate. This way, the main code remains simpler and highlights only the core tasks. One of the user-defined functions is USPTO graph dataset function. This dataset class takes a CSV file of chemical reactions, parses each reaction into reactants and product smiles, converts them into molecular graphs using another function called smiles_to_graph function, and then returns them as tuples that can be fed into graph neural network. In short, this function processes 40,008 USPTO reaction entries and produces batches of reactant product graph tuples, as shown in here, where each tuple contains one reactant graph and one product graph. The collate_pair function takes a batch or a list of tuples and transposes into two separate tuples using the zip** batch command. In other words, it returns one list containing the reactant molecule graphs and another list containing product molecule graphs. It is shown here. The MolR code uses collate_pairs function within data loader function from the torch_geometric.loader module. This wraps the datasets into a data loader that handles batching and shuffling. The batching behavior is defined by collate_pair function so that each batch returns a list of 32 reactant graphs and a list of 32 product graphs, as shown here. Now we instantiate the graph neural network, or GNN. In other words, we have a model ready to encode reactant and product graphs into numerical vectors using the reaction GNN class. Next, we set up an optimizer which will update the GNN's parameters during training. Now we call model.train function to begin training. We use a for loop over epochs to perform resampling and another for loop to iterate over each batch, which contains 32 reactants graphs and 32 product graphs. Each batch is processed by graph neural network, producing learned vector representations for the molecules. These vectors for reactants and products are used to compute the contrastive loss via the mol_contrastive_loss function, which minimizes the distance between the matching reactants and products while maximizing the distance between non-matching pairs. Next, the code backpropagates gradients and updates the GNN's weights using the optimizer. At the end of each batch and each epoch, the MolR code saves the locally trained results in the empty out folder. Okay, let's walk through the MolR training code. First, we import the custom modules and Python libraries. Second, we read and parse the USPTO dataset, converting the reactions into molecular graph using the USPTO graph dataset function and smiles to graph function, which is external to the training code. Third, we prepare the dataset for batching and shuffling. Here we use a batch size of 32 reactant product pairs. We're using collate_pairs as the method. The collate_pair function organizes each batch into a list of 32 reactants and a list of 32 products. First, we instantiate the graph neural network model and set up the optimizer for training. Now we train the model by using model.train function. We're iterating epoch by epoch over each batch of the reactant and products in the loader. Each batch is first processed by the GNN model, converting the reactants and products into vector representations. Next, we calculate the loss using the contrastive loss function with a margin of 0.5. This is another external function, contrastive loss. This function computes positive scores for the matched pairs and indicated by index I, and the negative scores for unmatched pair, which is indicated by I, j. Importantly, the maximum negative score is selected from the batch to focus on the hardest negative products for each reactant. This is the product most similar to the reactants and therefore most likely to confuse the model. The code then backpropagates gradients and updates the model weights using the optimizer, and we calculate the total loss by summing the loss value. Finally, at the end of each batch and each approach, the MolR code saves the locally trained results in the empty out folder. Okay, let's run the code by clicking the play button. Now the run is complete and we have the similarity score for the reaction of ethanol turning into acetaldehyde. As shown, the MolR chemical-reaction-aware molecule embeddings uses GNNs as molecule encoders. By training the GNN encoder to minimize the residue of the sum of reactant embedding and the sum of product embeddings close to zero for a specific reaction, the model implicitly learns exactly what changes or what does not change at and around the reaction center, which is the implicit learning. The model applies positive and negative samplings to guide optimization. This helps organize the embedding space by grouping chemically equivalent molecules together while separating non-equivalent combinations. Since the region of a molecule far from the reaction center don't affect transformation, knowledge from one reaction can generalize to a broader class of similar reactions. For example, what MolR learns from the reaction between propanol and propionic acid can extend to alcohols and carboxylic acid. In this way, MolR implicitly learns reaction templates, which are key for generalizing to unseen reactions. Okay, this is the end of the session. Thank you for your attention. I hope you found the session engaging and informative.